There is something people never say at a launch. They watch the countdown, they cheer at ignition, they share the footage of the rocket climbing into the sky, of Earth shrinking in the window, of 4 people doing something no human being has ever done in over half a century. And none of that is wrong. All of that is worth celebrating. But there is a part of the story that gets left out. Before Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen climbed into that capsule, before a single bolt was turned, before a single line of flight software was written, people died. Quietly. In accidents. In fires. In spacecraft that were not ready. In jet trainers and altitude chambers, and on launch pads where something went wrong that nobody believed would go wrong. The hatch on the Orion spacecraft opens in seconds. There is a reason for that. The pressure suits the crew or during launch would have kept them alive if the cabin lost pressure. There is a reason for that too. The solid rocket booster joints were redesigned from the ground up. The heat shield material was chosen specifically to avoid a particular failure mode. Every one of those decisions has a reason. The reasons have faces. Artemis II did not begin on April 1, 2026. It began with a coffin. Gus Grissom had already been to space twice. He was one of the 7 original Mercury astronauts, the men who defined what American spaceflight looked like in its first decade. He was blunt, technically brilliant, and deeply skeptical of the spacecraft he was about to climb into. His crew had been so frustrated with its quality that they posed for a photograph with their heads bowed in prayer and sent it to the program manager with a note that read, "It isn't that we don't trust you, Joe, but this time we've decided to go over your head." Ed White had walked in space, the first American to do it, tethered to Gemini 4 20 miles above the Earth, moving through the vacuum on a jet gun. He was so unwilling to come back inside that Mission Control had to order him 3 times. Roger Chaffee was 31 years old and had never been to space. He had spent years working toward this mission. January 27, 1967 was supposed to be a rehearsal. No fuel in the rocket. No launch. A countdown simulation inside the Apollo 1 command module at Pad 34, Cape Kennedy. Nothing was supposed to happen. The capsule was filled with pure oxygen, slightly above atmospheric pressure. This had been the practice since Mercury. Pure oxygen simplified the life support system, and it had worked. Nobody had yet run the numbers on what a cabin full of pure oxygen would do if something ignited inside it. The test ran long. Communications kept cutting out. Grissom's frustration came through the radio. If we can't talk between 3 buildings, how are we going to talk to the moon? At 6:31 p.m., a spark found the oxygen. The ignition source was a frayed wire bundle under Grissom's seat. Pure oxygen under pressure does not burn. It detonates. Nylon netting, Velcro, foam, padding, materials that would barely smolder in a normal atmosphere became fuel. The cabin temperature reached thousands of degrees in seconds. Chaffee's voice came over the radio. Fire. Then, we have a bad fire. Then silence. Ed White tried to open the hatch. It opened inward, fastened with 6 bolts that required a ratchet, turned once at a time from inside, designed to take 90 seconds under normal conditions. The internal pressure was rising. It was not possible. 27 technicians on the pad tried to reach them through the heat and smoke. By the time the hatch opened, 5 minutes after Chaffee's first call, all 3 men were dead. Their suits had fused to the interior of the cabin. It took 6 hours before the bodies could be removed. The investigation found over 1,400 safety problems with the spacecraft. 1,400 in one vehicle, already on the launch pad. North American Aviation, the contractor, had known about many of them. NASA had known about some. The program had been moving fast, and the problems had been accumulating quietly while everyone focused on the schedule. NASA halted crewed Apollo flights for 20 months. They redesigned the hatch to open outward in seconds. They replaced the pure oxygen ground atmosphere with a nitrogen-oxygen mix. They stripped every flammable material from the interior and replaced it. They rewrote the wiring standards. Flight Director Gene Kranz told his team afterward, We were too focused on schedule, and we blocked out every problem we saw. Every element of the program was in trouble, and so were we. Apollo 11 landed on the moon 2 years later. The command module that carried Armstrong, Aldrin, and Collins home was a direct descendant of those 20 months of rebuilding. The quick-release hatch, the fireproof interior, the mixed atmosphere during ground operations. None of it existed before 3 men burned on a pad in Florida. Launch Complex 34 was decommissioned in 1969. It has never been demolished. It stands on the Cape today, slowly rusting under wild pepper trees, a faded sign reading "Abandoned" in place. 3 granite benches sit at its base, one for each man. Every January, families return to leave flowers. The Orion spacecraft sitting on top of the SLS rocket on April 1, 2026, used a quick-release hatch system and fireproof interior materials and a mixed ground atmosphere because of what happened on Pad 34 on January 27, 1967. 3 months after Apollo 1, on the other side of the world, a cosmonaut named Vladimir Komarov launched on a spacecraft he had been told was not ready. Engineers had documented over 200 technical faults with the Soyuz 1 before launch. Quality control inspectors had raised formal objections. The spacecraft had problems with its solar panels, its attitude control system, its parachute deployment mechanism. The engineers who knew the vehicle best believed it should not fly. None of it changed the decision. A Soviet national celebration was scheduled. Political pressure won. Komarov's backup was Yuri Gagarin, the first human to orbit the Earth, the most celebrated person alive in the Soviet Union. Gagarin had tried to take the flight himself, believing the leadership would never risk his life and would cancel the mission. It didn't work. When people asked Komarov why he didn't simply refuse to board, his answer was direct. If he refused, Gagarin would go in his place. He would not do that to his friend. So he strapped in, knowing. Soyuz 1 reached orbit with one solar panel stuck closed. The attitude control system failed. The spacecraft spun. Komarov spent over a day fighting the vehicle, trying to stabilize it, trying to align it for re-entry. He managed, barely. Soyuz 1 hit the atmosphere on the correct trajectory. The main parachute failed. The container had been manufactured incorrectly. The interior walls too rough, coated with a compound that prevented the parachute lines from deploying cleanly. The reserve parachute tangled with the partially deployed main. Soyuz 1 hit the ground at approximately 89 miles per hour. The recovery team found a crater and a mass of charred metal. Komarov was barely identifiable. He was 40 years old. Yuri Gagarin died 11 months later in a training jet crash. He was 34. The Soviet program was redesigned around what had failed. Parachute manufacturing specifications were rebuilt from scratch. Quality control procedures were overhauled, and every spacecraft that followed, Soviet, Russian, and eventually the entire global crewed spaceflight industry, carried within its parachute system the technical record of what happened above the Orenburg Steppe in April of 1967. 4 years later, 3 more, Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsiev, had just spent 22 days aboard Salyut 1, the world's first space station. They had broken every human endurance record that existed. The mission was complete. The spacecraft was performing normally. The re-entry was going exactly as planned. A pressure equalization valve opened prematurely. They were at 168 kilometers altitude in the vacuum of space. The valve was designed to equalize cabin pressure during the final moments before landing. In atmosphere, near the ground where it was safe, it opened 168 kilometers too early. The 3 cosmonauts were not wearing pressure suits. The Soyuz had been designed with a brutal compromise. The cabin was too small for 3 suited men, so the suits were removed. This was a known limitation, a documented trade-off, accepted because previous missions had flown safely without suits and nothing had gone wrong. The valve that opened prematurely was located beneath the cosmonaut seats. There is evidence they found it and attempted to close it manually. Under ideal conditions, that would have taken several minutes. They had less than 60 seconds of consciousness. Within 30 seconds of the valve opening, the cabin pressure dropped toward vacuum. Within 2 minutes, all 3 men were dead. The spacecraft continued its descent on autopilot. The parachutes deployed. Soyuz 11 touched down in Kazakhstan with textbook precision. When the recovery team opened the hatch, they found 3 men still in their seats, still strapped in, exactly where they should have been: blue, cold, silent. The capsule had launched perfectly. The crew had been dead for 30 minutes. The Soviet space program halted for 2 years. When it resumed, the requirement was absolute: pressure suits during launch and re-entry, always, for every crew member, with no exceptions. The Soyuz was built to carry 2 cosmonauts instead of 3 to create the space for both suits. That requirement has never been modified. It applies to every crewed spacecraft flying today, including Orion. The orange suits the Artemis II crew wore at the SLS climbed off the pad on April 1, 2026. The suits that would have kept them alive if the cabin had lost pressure during ascent exist because of a valve the size of a fist that opened 53 years ago at the wrong altitude. On August 2, 1971, about a month after the Soyuz 11 funerals, Apollo 15 astronauts David Scott and James Irwin placed a small aluminum figurine and a plaque on the surface of the moon at the Hadley Apennine landing site. The plaque listed 14 names: 8 Americans, 6 Soviets: Grissom, White, Chaffee, Komarov, Dobrovolsky, Volkov, Patsiev, and others who had died in jets and altitude chambers and training accidents whose names the public largely did not know. 2 superpowers that had spent years competing to reach the moon left their dead side by side on its surface. The figurine is still there. It will be there for millions of years. There is no wind on the moon, no rain, no erosion. The names on that plaque will remain legible long after every building on Earth has turned to dust. 3 more names belong on it now, and the list of people whose deaths contributed to the knowledge that keeps astronauts alive, and most of them not astronauts at all, runs much longer. The space shuttle program was built on a promise: space travel would become routine, reusable hardware, frequent launches. The spacecraft that operated more like a commercial airliner than a one-time rocket. The goal was to make the extraordinary feel ordinary. Challenger's crew of 7 included Krista McAuliffe, a high school teacher from Concord, New Hampshire, selected from over 11,000 applicants to be the first civilian in space. Millions of American schoolchildren were watching the launch from their classrooms on January 28, 1986. The night before, engineers at Morton Thiokol, the company that manufactured the solid rocket boosters, were on the phone with NASA until midnight. They had data. The rubber O-ring seals at the booster joints were sensitive to temperature. Below a certain threshold, they lost flexibility. They might not seal properly against ignition pressures. The engineers recommended holding the launch until the temperatures rose. NASA managers pushed back. There was pressure to fly. There had been delays. The program needed to demonstrate its reliability. The engineers were asked to prove that it was unsafe to launch, rather than to prove that it was safe. That distinction mattered. Thiokol management overruled their own engineers. The launch was approved. It was 36 degrees Fahrenheit on the Cape that morning. Challenger lifted off at 11:38 a.m. 73 seconds later, an O-ring in the right solid rocket booster failed. Hot combustion gas burnt through the joint, reached the external fuel tank, and the vehicle broke apart. Francis Scobie, Michael Smith, Judith Resnick, Ellison Onizuka, Ronald McNair, Gregory Jarvis, Krista McAuliffe. The investigation found that the crew cabin survived the initial breakup intact. Emergency oxygen packs had been manually activated. At least some of the crew were conscious and functioning after the shuttle came apart. The cabin fell for 2.5 minutes before hitting the Atlantic at 321 kilometers per hour. The engineers had been right. They knew it the night before. The Rogers Commission investigation named what had happened: normalization of deviance. O-ring erosion had been observed on previous shuttle flights. Each time the flight had ended safely, and the damage had been reclassified as acceptable. The warning built up slowly across mission after mission until the morning it killed 7 people. The commission found that the organizational dysfunction that allowed this was systematic and deep. Not an accident, a pattern. The shuttle was grounded for 32 months. NASA rebuilt its safety infrastructure. Crew pressure suits, which had been removed from the shuttle program to make flights feel more routine, were reinstated. The booster joints were redesigned with new O-ring configurations and additional backup sealing. The solid rocket boosters on the Space Launch System are derived from the shuttle design. Every joint connecting their segments was engineered with Challenger's failure as the explicit design boundary. The SLS boosters that pushed the Artemis II crew off the pad on April 1st carry within every seal the record of 7 people who died because the seal failed once before. 17 years after Challenger, the same pattern, 7 more. Space Shuttle Columbia launched on January 16, 2003. During ascent, a piece of foam insulation broke away from the external tank and struck the reinforced carbon panels on the leading edge of the left wing. Launch cameras recorded the impact. Engineers reviewing the footage flagged it. A request was submitted to obtain satellite imagery of the wing to assess the damage. The request was denied. Management concluded there was nothing that could be done from orbit anyway, and that the foam was unlikely to have caused serious damage, partly because foam had separated on previous shuttle flights without consequence. An engineering team ran independent damage assessments and determined the situation might be serious. Their analysis was not escalated to mission management. A contingency plan exploring whether the crew could shelter on the International Space Station was drafted and then set aside. For 16 days, the crew of 7 conducted science experiments. They had no way of knowing their left wing had a hole in it. Rick Husband, William McCool, Michael Anderson, David Brown, Kalpana Chawla, Laurel Clark, Ilan Ramon, the first Israeli astronaut, a former fighter pilot who had flown on the mission that destroyed Iraq's nuclear reactor in 1981. On February 1st, Columbia re-entered the atmosphere. Within minutes, temperature sensors on the left side of the vehicle began recording anomalies. A few degrees warmer than expected, then more. The internal structure of the left wing melted. Superheated atmospheric gas had entered through the hole and was burning the vehicle from the inside. Columbia broke apart over Texas and Louisiana at 60 kilometers altitude. The debris field covered 2 states. Recovery teams eventually recovered over 82,000 pieces, approximately 38% of the vehicle's dry weight. The other 62% burned in the atmosphere above people's homes. The Columbia Accident Investigation Board's conclusion was devastating in its precision. NASA had not changed after Challenger. The same culture that had allowed O-ring erosion to be normalized had allowed foam strikes to be normalized. 17 years and 7 deaths later, the board wrote that the 2 disasters shared an identical root cause, an organization that had learned to redefine its anomalies as acceptable until they weren't. The shuttle program flew 22 more missions, then ended in 2011. 14 astronauts dead in 2 catastrophic failures. The heat shield on Orion is an ablative material specifically designed to avoid the tile-based vulnerability that destroyed Columbia. When Artemis I flew in 2022 and engineers found unexpected erosion in the ablative material after splashdown, the program stopped. Investigated for nearly 2 years, changed the re-entry trajectory, delayed the crew launch repeatedly from late 2024 to February 2026 to April 2026, because the engineers would not fly until they understood what they had seen. Every one of those delays is the institutional memory of Columbia, still functioning, still doing its job. Those 4 disasters account for most of the names people know, but the education that built Artemis II required more than 4 disasters, and some of the most significant deaths happened far from any launch countdown. Valentin Bondarenko was 24 years old. He was a member of the Soviet Union's first cosmonaut class, the same group that produced Gagarin. In March 1961, 3 weeks before Gagarin's historic flight, Bondarenko was in the final hours of a 10-day endurance test inside a pressure chamber filled with pure oxygen. He cleared a sensor pad with a cotton ball soaked in alcohol and discarded it. It landed on a hot plate. In a pure oxygen environment, there was no gradual ignition. He died of his burns 8 hours later. The Soviet government classified his death for more than 2 decades. The world was not told that the celebrated Soviet space program had already killed one of its own before it put anyone in orbit. Theodore Freeman, NASA astronaut, died in October of 1964 when a goose struck the canopy of his T-38 jet trainer, shattering it and flaming out the engines. He was 34. He had never been to space. Charles Bassett and Elliot C., the original prime crew for Gemini 9, were killed in February 1966 when their T-38 clipped a building during a low-visibility instrument approach to the McDonnell Aircraft plant in St. Louis. Both men ejected. Neither was high enough for the parachute to open. They were replaced by Tom Stafford and Gene Cernan, who flew the mission 4 months later. Clifton Williams died in a T-38 crash in October of 1967. Robert Lawrence, the first African-American astronaut selected for the Air Force Manned Orbiting Laboratory program, died in an F-104 crash in December of the same year. He was 32. He was never publicly acknowledged as an astronaut until 1997, 30 years after his death. Michael Adams flew his X-15 hypersonic research aircraft to 266,000 feet in November 1967, high enough to qualify for astronaut wings. A flight control malfunction put the aircraft into a hypersonic spin on the way down. It came apart at 60,000 feet. Michael Alsbury was the co-pilot of Spaceship Two on a powered test flight in October 2014, when the feathering mechanism deployed prematurely. The aerodynamic forces destroyed the aircraft at 50,000 feet. He was 39. Each of these deaths was a data point. Every flight envelope restriction, every ejection system protocol, every crew escape requirement that has been refined since the 1960s carries the fingerprint of someone who ran out of altitude or time while the limits of a new system were still being discovered. On October 24, 1960, at the Baikonur Cosmodrome in Kazakhstan, an R-16 intercontinental ballistic missile exploded on the launch pad during pre-launch testing. The blast and the fire that followed killed approximately 120 people. Military personnel, propellant engineers, technicians. Marshal Mitrofan Needlin, the commander of Soviet rocket forces, who had positioned himself roughly 65 feet from the missile to pressure his teams to work faster, was killed in the initial explosion. The Soviet government classified the entire disaster. The outside world did not learn about it for decades. Another explosion at Baikonur in 1980 killed 48 more. These were not astronauts or cosmonauts or test pilots with names on monuments. They were the people who actually built the machines, the welders, the propellant handlers, the technicians who worked the night shift during a countdown and whose only ambition is to do the job and drive home. Their deaths are part of the technical record of how launch infrastructure is made safe, how far back personnel must stand, how fueling procedures must be sequenced, how blast barriers must be positioned. They are embedded in the safety protocols at Kennedy Space Center in ways that are real and functional and anonymous. As of launch day, 791 people had traveled to space. 19 had died doing it, a fatality rate of about 2.4%. Include training accidents and ground tests, the count of deaths related to spaceflight preparation rises above 30. Include the technicians and workers killed in launch accidents, the classified deaths at Soviet cosmodromes, the unnamed workers vaporized or poisoned at facilities across 6 decades, the number reaches well past 150. Every single one of those deaths changed something about the way the next vehicle was built. The launch abort system mounted above the Orion capsule, the tower that would have pulled the crew free of the rocket in a fraction of a second if something had gone catastrophically wrong during ascent, was built from the lesson that there was no way out of a burning capsule at Pad 34. The quick-release hatch, the fire-resistant materials, the emergency escape architecture, all of it traces back to January 27, 1967. The pressure suits the crew wore trace back to a valve in a Soyuz descent module that opened at the wrong altitude. The solid rocket booster joints trace back to a cold morning on the Cape when the engineer's data was overruled and 7 people fell from the sky. The heat-shield design and the culture of not normalizing anomalies trace back to 16 days of experiments conducted by people who did not know their spacecraft had a hole in the wing. And the 3 launch delays, the rollbacks, the investigations, the months of additional analysis trace back to every time in the history of the program that someone decided a known problem was probably fine and was wrong. That is not abstract. That is a specific, traceable, documented chain of cause and effect that runs from a burning capsule in 1967 to a spacecraft lifting off the pad in 2026 and returning its crew safely to the Pacific 9 days later. The crew named their Orion spacecraft Integrity. They said it honored the trust between the teams across NASA, ESA, and dozens of contractors who had built it together. Over 300,000 components integrated into a single vehicle by thousands of people working across different countries and time zones. The name acknowledged what it had taken to bring all of that together. But Integrity also describes something structural, a material that holds under load, a structure that does not crack at the joints, a system that remains whole when the pressure builds. The spacecraft holds because of everything that failed before it. Every cracked weld, every failed seal, every fire and explosion and spin that could not be recovered from. All of it was studied, documented, and stitched into the next design. The scars are structural. The failures are load-bearing. Gus Grissom said something after his Gemini 3 flight in 1965, 2 years before he died at Pad 34. If we die, we want people to accept it. We are in a risky business, and we hope that if anything happens to us, it will not delay the program. The conquest of space is worth the risk of life. He was joking about the photograph sent to the program manager with the prayer pose. Then, 2 years later, he wasn't joking about anything anymore, and the program did not stop. It changed, it learned, it flew again. The 4 people who climbed into Integrity on April 1, 2026, carried more than instruments and cameras. They carried the resolved failures of every person who came before them and did not make it home. Grissom, White, Chaffee, Komarov, Dubrovlovsky, Volkov, Patsiev, Challenger 7, Columbia 7, the test pilots and trainees and technicians whose names most people have never heard. They carried all of it 695,081 miles from Earth to the moon and back. And because of all of them, they came home. Artemis II made it home. And if you want to understand everything those 4 people actually experienced, from the moment they left Earth to the moment they landed in the Pacific, watch Artemis II, the complete story, start to finish. Everything.